would like to briefly review the old unit load system and show the manual type operations that have been automated. A typical day started with the operator receiving their daily select sheets. These sheets indicated the piece part com codes, quantity to be selected, and rack locations of the material to be selected. The operator then reviewed all the selects, boarded the crane, and proceeded to start the selecting process. The operator would move the crane to the first location. Manual operation of the crane was significantly slower as a result of the crane speed being less and the operator having to manually locate the crane both horizontally and vertically prior to picking up a pallet. The operator then checked to see that the material matched the select sheet, removed the pallet from the storage rack, and brought the material forward to the selecting area. Again, the operator must manually locate the crane horizontally and vertically prior to depositing the load at the pick station. After selecting the correct quantities and placing them on a pallet, the operator would then adjust the inventory by inputting the information of the transaction on the terminal aboard the crane. The operator would then return the original pallet to its previous location and proceed to the next select location. This method required one operator per crane, thereby requiring 10 crane operators per shift. From mid-1991 through 1992, a major redesign of the unit loader system was embarked on. The new system was nicknamed Roller City. The design criteria demanded a flexible, versatile, automated, safety-oriented system which would maximize material throughput and be fully compatible with the future e-stock material handling processes. This new system was designed to allow one operator or as many as 5 operators to control all stocking and picking functions. This system contained over 580 feet of 3,000-pound capacity pallet roller conveyor, 145 Honeywell photo eyes, 130 Honeywell limit switches, 106 Allen Bradley motor starters, and 35 chain transfer devices. Material to be stored in this pallet storage system is deposited by fork truck on a sleigh pallet at the pallet input station. After the fork truck has placed the material on the sleigh pallet and has pulled back, the driver pulls a cord which indicates to the system that the pallet is ready to be moved. Each of the sleigh pallets, automatically dispensed from the pallet storage system, has a unique pallet ID barcode label on it. The input operator uses the barcode scanner to enter the barcoded sleigh pallet ID and the barcoded material stocking label ID. The input operator then indicates whether the pallet should go to the stretch wrapper. The inline stretch wrapper is located on a conveyor spur and is computer controlled. This machine is capable of handling 50 pallets per hour. If the pallet is not wrapped, or after the pallet has been stretch wrapped, it is sent to the sizing station. The sizing station checks for over height, over width, and over length pallets. Pallets not meeting any of the 3 checks are returned to their point of origin for correction. After the pallet passes the sizing station, the pallet is given a crane assignment by the unit loader computer. Crane assignments are based on a modified round-robin algorithm which assigns the load to a crane on a rotating basis, adding 1 to the previously assigned crane. Use of this round-robin technique tends to spread product across the crane aisles. The unit loader computer then finds an empty location for the pallet in the assigned crane aisle. Locations are selected to minimize the time needed to move to the location. As the horizontal motors move faster than vertical motors, the system uses the zone map for determining the closest empty location. This storage technique will minimize the amount of movement of the stacker cranes. After the pallet has been stored, a message specifying the pallet ID and the storage location is sent from the unit loader computer to the Moves SC computer. The Moves SC system is responsible for keeping track of first in and first out inventory of these pallets and for proper generation of retrieval requests by pallet ID. Retrieval requests are downloaded periodically from Move's SC system to the unit loader system. As soon as they are downloaded, a communication process adds the request into the unit loader database. Each request has an associated priority. Actual pallet deliveries out of the unit loader to the picking station depend on the order in which they were received, the concentration of requests for a given aisle, priority levels involved, and aisles being offline. If the designated picking station does not have room, the computer will direct the stacker crane to retrieve the pallet and deliver the pallet to the next available online picking station. When the pallet arrives at the picking station, the select request information is displayed on the pick operator's terminal. The operator uses the barcode scanner and enters the slave pallet ID to verify that the correct pallet is in the picking station. There are 3 methods of picking material from the unit loader. Method 1 occurs when all the material on the slave pallet is required to fill the select. The operator then can route the entire pallet to the full pallet out station. Method 2 requires the operator to place the picked material onto another pallet for possible accumulation prior to being removed by a fork truck. Method 3 specifies the operator to place the picked material into an empty tote. Empty totes are retrieved from the overhead tote conveyor. After placing the material into the tote, the operator places the tote onto the vertical material lifting system and is automatically sent to the shortage fill and kitting areas. After material has been picked, the operator then enters the quantity picked and a barcode ship label is printed. After the transaction is complete, a Pick Complete message is sent to the Move's SC system. The unit loader computer does a look-ahead scan of the remaining requests for additional select requests for the same material. If additional requests exist, labels are printed and additional requests are also picked prior to the material being returned to the racks. If the remaining load requires it, the operator can designate that pallet to be routed to the stretch wrap machine prior to being returned to the unit loader. The pallet is then released to be restored in the storage racks. The pallet is sent to a sizing station prior to being stored. When the pallet passes the sizing station, the unit load computer assigns the aisle for the pallet to go to using the modifying round-robin algorithm similar to the initial storage process. The following is an explanation of the software and controls of the unit load system. The software was designed to allow the operating personnel, engineering personnel, and the maintenance technicians to control all functions of the entire unit load system from a terminal. The software and controls of the unit loader consists of a 3-level architecture. The highest control level provides functionality for tracking and control of material. This functionality is provided by Move's SC, which is a Unix-based AT&T Prism software residing on a 3B2. This system links to Impact, which is the mainframe MRP system via RJE and 3270 emulation. As requests for material are communicated from Impact, Moves determines a specific pallet ID to pick from based on FIFO and other considerations. These pallet IDs and the corresponding part ID information are then communicated to the SuperHat, head of aisle terminal, via TCP/IP. The SuperHat is a Unix-based AT&T Star server which is responsible for the following: management of the pick queue to optimize system throughput and execute priorities of items within the pick queue, coordinate activity between cranes, conveyor, pallet stacker, and stretch wrapper, provide the user interface, and keeps Moves SC informed about the status of the work in the pick queue. The third control level provides control of the cranes and front-end conveyor. This is performed by DOS-based industrial-hardened 286 controllers. This control level is where the software interacts with the various input-output elements to perform machine control. Each of the 10 cranes has a 286, as does the front-end conveyor system. Each of these machines take their command directly from the SuperHat via RS-232. All electrical components and circuit boards used in the unit loader are available off the shelf from third-party vendors. Processor boards, Input-output boards, motor starters, and other electrical components are available from vendors like Allen Bradley, Gray Hill, or Prolog distributors. Alternate brands of products can be substituted for components in the system. The Prolog controller and input-output cards, for example, uses a standard bus and could be replaced by cards from other manufacturers. The new software also provides 47 different programs with screens to aid the operator and maintenance technicians in controlling and maintaining the unit load system. The following are just a few examples of these 47 screens. The crane position display screen shows the current horizontal and vertical position of the crane graphically. Vertical position is shown bottom to top. Horizontal position is shown left to right. The current position is indicated with a small colored circle. As the crane changes position, new circles are drawn to give the appearance of a wide line. When the commanded position is reached, both horizontally and vertically, two concentric white circles are drawn. The crane status display shows the status of the crane in real time. This screen shows the command presently being executed, the last message from the host, horizontal speed, vertical speed, crane position, and status of all input-outputs aboard the crane. The discrete input-output area of the screen displays the status of individual input-output bits. This screen allows the maintenance technician to change the on-delay time value of the load presence photocell. When a load enters a zone, the drive motor continues to run until a photocell is blocked and its timer has expired. The stopping position of a load in a zone can be adjusted by setting the on-delay time value of the photocell that controls that zone. The units used are time ticks of the 286 processor, each tick equaling 55 milliseconds. Thus, if it is desired that a motor run for 1 second after the photocell is blocked, the timer should be set on 18. This screen shows which loads are in motion from one zone to the next. When a release is active, it will display in red. An active release means that the motors and solenoids associated with those zones should be operating to move the load from zone to zone. If no load movement is apparent, then a physical problem exists, such as a limit switch is not working, a photocell is not working, or a motor has timed out. This screen shows a zone layout of the entire conveyor system. Empty zones are displayed in gray. Zones which contain a load are displayed in blue. Each zone that is occupied will display the load's ID, the load's destination, and the record number used to identify that load in the conveyor system database. This display is dynamic and will update automatically whenever the display information changes. Unit load software and controls have far exceeded all expectations, to the point that our mini-load ASRS system will be retrofitted with the same control architecture. This will improve the level of integration as well as reduce the software support resources required between the mini-load ASRS and the unit loader.